Hello, welcome back to the session. And today we'd like to start our new part 2, local strengths analysis part. And as you could see here, we'd like to cover topic 10 today here. And then actually topic 10 to 12, three topics are related to the column buckling methods. So after that, we will learn about the truss by joint method and section method. And the last topic will be the statistical analysis. But personally, I do believe that this part, especially for the column buckling part, should be considered as one of the important topics for us. So let's get it. So the aim of this lecture is we could keep and understand about the elastic buckling behavior for our structure. In here, structure means we will learn based on the beam or the column, the 1D members, but later these could be expanded to our ship structures, like for example, this is just like double hull, oil tanker, midship section, and for example the deck or outer bottom, inner bottom, or side shell. We can see like this is the combination of the plate and stiffener. So we call the plate stiffener combination model, which means that we can split the cut all the stiffened panel based on the one stiffener and one plate, so that the shape will be like this: stiffener and plate. So what's that? It looks like the beam that we have learned before. So that is reason why we will focus on this 1D beam or the column first, and then the outcome of this lecture might be we could be able to describe the equilibrium status, and the beam, the column, will be subjected to the axial compression. In the case of beam, that is subjected to the bending, but here we are talking about column subjected to the axial compression. So we will understand about the buckling failure mechanism and the mode of the column, beam column, and that can be expanded to the stiffened panel that I explained earlier. And we should be able to consider the various types of the boundary conditions, or we call the end constraint, and we could be able to drive all types of the governing equations, equilibrium, and we will learn about what is the Euler critical buckling load, about the pin and column, and why this Euler critical buckling load is important for us. So this is brief introduction of our topic 10, but that will be important for us to start topic 11 as well as 12. So let's start it. So as you could see here, you can see one video material. So so I have added so alright, as you can see here in this slide, I have prepared one simple video clip, but before that I'd like to ask you to think about how do we think about load carrying capacity. That will be covered here in topic 10, and continuously we should be able to think about the effect of boundary conditions that will be explained in topic 11. But this video clip will explain almost everything for us. And one more thing is, how do we think about the effective length and failure shape to be covered in topic 12. So before we move on, let's see the video. Can you see the video? I will show you one more time. So basically they have two different column here, the left hand side and right hand side, and what you need to focus is they will put some steel powder from here, the right hand side, the column first, and then they will put more and more powders. So what we need to see is that the behavior, the buckling behavior or the deflection shape of the column here. So let's have a look again. They are putting some powder now. You see here, so it is, which means that apply the force is increasing, and I stopped here. You have to understand. You can see here this boundary condition is actually pin-pin condition, or we can say that this is simply supported boundary condition, right? And please remember the shape of the column. This is symmetric perfectly, and then this is pin-pin or simply supported condition, and this amount of the steel powder used, and then they will move this to here. And again, from here we should understand that this is already buckled, right? So let's have a look. And they move this to the left, and then they put additional steel powder here, and then here we have to focus on this shape. Okay, I will stop here again. And what I want to talk is those two, as you see here, the used column here and there, those two are exactly same material, same geometry, same length, but let's think about load carrying capacity. What happened here? Why the left hand side, the column can carry additional load? This is my first question, and we will focus on that. So the reason is, as you could see here, originally we could carry this amount from here, and then they put additional here. So what makes the changes? What makes the difference? So I would say that the main difference is boundary condition here. As you see here, this was simply supported, and then here this is still the same. This is simply supported or pin condition, but here this is not the simply supported. I would say that this looks like clamped or fixed condition. So we simply change one boundary condition at the bottom from the simply supported to the fixed condition, and then we could see this much of the additional load or the weight could be covered by our column. So as a structural designer, we can think carefully on this matter because we have used exactly same material, same geometry, but we simply change the boundary conditions, and then almost 2 times better capacity has been confirmed by this test. So effect of boundary condition, you can now simply briefly understand about it. Okay, and mathematically we will try to drive it, and then think about effective length and failure shape. Right, at the end of this lecture I will briefly show you what is that. So let's move on. So where we are, previously we've learned about the material curve from the marine mechanics. So as you see here, this is quite common. Apply the load first divided by area so that we can get normal stress, and then this is epsilon strain, and we learned about Hooke's law, and we could obtain it from here, right? And then topic 9.5, if I'm not mistaken, we've learned about this one, about this is subjected to the tension, so that once the force is increased or stress is increased, and then till yield stress, and then it will start to move to the right, and we can consider this is ultimate strength. What I'm talking about is this is 1D element, isn't it? So this is actual elongation curve, this is epsilon, but again this is for the tension behavior. But if you consider the compression, the shape will not be like that. It should be like this. So that is reason why we are here, and we will discuss about that. And question, let's consider two bars of the same length. Number one, this is exactly same length, same material, but different cross section as you see here. But again, this is exactly same material used, and cross-sectional property in terms of the moment of inertia is not same, but area is exactly same. As you see here, the area sectional property is 3TB, and this is also area is BT times 1, 2, 3, 3. So that is exactly same, but here, this is the key point, moment of inertia value, that must be different. And the question is, this is the case under actual tension. So which column will fail first? And if we consider actual compression, what will be? That is more important for us. So in the case of yielding, that should be, the keyword is the tensile loading, and the plastic deformation should be considered, especially this one, tensile loading for yielding condition. And in the case of buckling, in this collapse, which means that we need to think about compressive loading. So frankly speaking, this is our main target from these topics, topic 10, 11, and 12. All right, so continuously we are talking about the buckling. Here, the question is why under axial loading, the column deflect in lateral direction. So as you can see here, previously we already see the video, watch the video, and once we apply the loading, axial compression, then of course this 1D element, the structure column, will be deflected this way, but apply the loading direction is here. So this is the first condition to define buckling. So axial compression applied to our structure, as you can see here, and our structure 1D column or stiffened panel will be buckled, but the direction is perpendicular to the applied load. This is 90 degree, isn't it? So this direction is perpendicular, and third one is suddenly. It is suddenly collapsed. So let me go back for you to understand it again. So last one, let's see the video again. So focus on the buckling behavior. They are increasing the load and then suddenly buckled like that. Even we change the boundary conditions, they can carry additional load, but it is also sudden behavior. It's like that, right? So let me go back to here. So actually, we will discuss about the buckling. We have defined buckling behavior by number 1, 2, 3 conditions. Instability problems will be covered by this topic. So what is instability? So you can see 3 different equilibrium conditions. First, stable. Second, this looks like first stable, second neutral condition, it is flat, and third one is it is also equilibrium conditions, but we call it this is looks like unstable. If we apply small amount of the load, that can make the move to the left, to the right. You know what I'm saying? So like here, we can see that this is our resistance in the positive way, and it looks like just like that. And we learned that this is epsilon, this is actual stress, and this part was elastic region. And if we apply the load, for example the tension or the compression here in this region, once we apply the load till here and then remove it, then it will go back to the original status, which means that we don't experience any plastic deformation. That's why we call it this is elastic region. So until here, before this region, we move our rock here and then remove the resisting force, then it will move down to the original status, original place. But if we move it at this point, then that will be unstable equilibrium conditions. But if we apply additional force and then they move to the another chapter like here, then it will be gone. You know what I'm saying? So previously it's like sharp transition condition as well. So previously, as you could see here, Sisyphus was forced to roll in big rock up a hill, as you can see here, but it rolled back to the origin, and then task was never finished, and he was forced to repeat it over and over again forever. So it is something like that. Based on these initial ideas, we can think about instability conditions like buckling methods. So instability. So structural response under axial compression, as you can see here, this is our column, and apply the force is axial compression. And then once we plot, axial shortening versus axial reaction force is here. This is compression, and this is, displacement. And you see here, this graph shows exactly similar as we seen before. So this slope represents stiffness, and this point should be considered as critical load that we call the buckling strength. This is not, we are not talking about actual tension, but this case is compression, right? So in the case of tension, the behavior was like that at yield point. You remember this, right? So let's move on. So the question is catch the load distribution, displacement curve for axial load and lateral deflection. You can see here, in this case, they are talking about there is no initial deflection, which means that our column is perfect, no deflection at all. But in reality, from the transportation or the manufacturing process, it should be deformed slightly or like that, right? So if our column is perfect, then once we apply the axial compression, then there will be no deflection from the beginning until here. So we apply the load, move it, load is increasing, but there is no deformation, no deflection. But at a certain point, like buckling strength passed, then it will start to buckle, which means that we gonna have lateral deflection suddenly like that, boom, right? So at here, buckling strength point, you can see that the deformation mode changes suddenly, and column cannot dissipate the external work done by apply the load through axial deformation and etc. Right? So as you can see here, this part before yielding, we can say that this is the stable equilibrium, because if we remove the load in this region, we will go back to here, original status, and this is the neutral equilibrium. So determination of critical load, how are we gonna make this, how we calculate it? So one of the famous scholar, Euler, he derived the brilliant, equations here, and almost 250 years ago, and to solve the elastic column methods subjected to the axial compression. So basically, you see here, the PE represent elastic force, and pi is pi 3.1415, something like that, and E, this represent material elastic modulus. E in general, E is 205,800 megapascal or 206 gigapascal used in shipyard. And I value, if let's say this is our column and sectional properties, we can calculate the I, the moment of inertia values, and L represent the length of the column. So it is pretty much simple, and later we will drive this one together. So he suggested and proposed this equation, and the question is, let's consider two bars, same length, same material, but different cross section, subjected to axial compression, exactly same amount of the axial compression applied. And as you can see here again, the sectional area A is 3 TB, and this is also 3B times T is 3BT. So exactly same amount of the material has been used. So here what we have is this equation, and in detail, pi same, and the material properties exactly same. So E, elastic modulus, must be same. Length of the length of the This is the length. This is the length. Exactly same. So what we need to focus is here. This one only. Isn't it? So in the case of I value, I in this case 1 over 12 bt cube. So 1 over 12 3t b cube. And in this case 1 over 12 b is t, and height is 3b. Sorry, this should be height cube. So this must be much better than this one. But here, what you need to remember is I'm talking about Ixx values. But in the case of moment, what I'm talking about is this column could be buckled in, think about it, this kind of column can be deflected in this way, number one, or this way, which means that we need to consider Ixx as well as Iyy. So we have to calculate those two for every cases, and then we need to select the minimum value. So that will be the direction of the buckling. You know what I'm saying? So if we are talking about if we are talking about Ixx at neutral axis, then the Ixx value is much better in this B case. So as well as Iyy case here, this is Iyy, and this is also Iyy, right? In this case, this might be better. So based on that, the deflection shape and the direction will be exactly, changed, definitely changed. So if you don't understand it, you can bring some kind of paper here and then use it. This looks like this B here, right? And then once we apply the actual compression, then it will be buckled like this way, like this way. Why it is not buckled that way? Because Ixx and Iyy calculation, you can compare it so that you can simply understand what I'm talking about, right? So let's move on. So buckling assessment. So we can calculate the critical buckling load, PE. And after that, this is the force, which means that we can calculate the stress values. How? PE over sectional area. So that will be elastic, buckling strength. So basically they are talking about the P. So based on these, they can do the assessment of the buckling. And then safety factor, we have to think about this. Safety factor, of course, that should be higher than 1.0, capacity and demand, right? COD is 1.0. At the same time, we can apply load factor, which means that applied load will be, and here, what I'm talking about is applied load will be overestimated so that we can secure additional safety margin. You know what I'm saying? For example, 10 or 100 Newton is applied, but sometimes it can be over like 110 Newton, something like that. We will overestimate the applied load. Structural capacity will be underrated, something like that. So that is basic concept of the safety margin and safety factor, load factor design. And Euler buckling stress, as I explained earlier, we can divide by sectional area so that we can get elastic buckling stress. So previously I've shown you this one, like Euler proposed this equation, and I have introduced this sectional area here. So divided by area so that we can get this equation and simplify it again based on E is not related here, and then bracket square so that we can simplify it one time here, and then we will bring this again, and here you should ask me R. What is R? What was it? R is I over A square, right? So please have a look, marine mechanics. So based on this, we can simplify this equation. So then now we are here, and then we will introduce one more important, very important concept here, lambda. Lambda. From here to here, please have a look by introducing this column slenderness ratio that is lambda here. I would like to suggest you to remember this equation. That will be useful for you to understand local strength analysis, not only for this module, but also for your future. So this is length and pi r, introduce I over A from the cross section, and this part is material properties, yield, and elastic modulus. So finally, we could be able to simplify the equation like that. And based on this, we can plot it. For example, so from this, we can simply plot. This is column slenderness ratio, and this will be elastic buckling strength over yield. So this will be the ratio based on the yield stress. So the maximum will be 1.0, and then we can get certain, equations here. So this looks like that, if I'm not mistaken. So this is actually Euler formula, and it's like that. This is Euler formula as I explained earlier, and this is the vertical axis 1, because we divided by the yield stress here, and then this is column slenderness ratio. So based on these column slenderness ratio values at here, at there, they define this is stocky column, this is intermediate column, this is slender column, something like that. At the same time, we need to remember this is proposed by the Euler, and based on this equation, we can determine whether the column will be buckled or not. Right? So I will introduce this again and again and again. So I've introduced what is the slender here, slender column, and stocky column, and intermediate part. You can see here, so in the case of slender, the linear buckling solutions and non-linear buckling solution for intermediate, but here it will behave like material instability by fracture or plastic flow. So that is the main difference. And later we will learn this in topic 11, but briefly I will introduce about that. So if someone asks us to how we're gonna sketch the buckled shape of the following columns, so as you can see here, we need to focus on the boundary conditions, like here. This is both ends pinned, the pin condition, and this is the fixed, this is fixed, and the other part, this is free. And in this case, this is fixed, and this is fixed, and this is fixed, and this is pinned. right? So 4 different boundary conditions, exactly same material used, but we want to know the shape once it buckled. So in the case of pimping condition, we've seen that will be like that. And then in this case as well, like fixed and pinned conditions, we've seen that it's like this. And the previous topic, I briefly introduced about boundary condition by using mathematical uh, formulations. Again, simply supported and clamped condition or fixed. Like deflection at here A and B, and slope and moment. If we go further, we can see like here, this is shear, and furthermore. So deflection, that should be 0 and 0. Slope, in this case, slope is unlimited, and in this case, we don't allow it. And based on this slope information, we can see that this moment for simply supported case, this is moment free condition. But here, the maximum moment will be applied to, not allow the slope here. So maximum, right? So please have a look on this, the simple beam theory part. And the shape will be, for example, like that. Simply supported, one fixed, one free, and fixed and fixed, and fixed and simply supported condition. As you can see here, based on these, we can provide this effective length information. In this case, the whole length L, actually 1L will be utilized effectively. But in this case, 2L. In this case, the shape is exactly not the right shape, so that this length effectively utilized is 0.5 L. And in this case, from here to here, effectively used length is 1.7 L in this boundary condition. So that is the main point, and based on this length information, we can simply substitute it. Actually, this will be revised to effective length, and that is like that. So just simply change the coefficient here, we call the K, so that we can still predict the elastic buckling force or elastic buckling strength as well. So reminder, in this lecture we learned about the elastic buckling of the structure, and now we're gonna able to describe these 3 status of equilibrium of column subjected to the axial compression, buckling failure mode. We discussed it in various end condition, boundary conditions, governing equations, and Euler equations based on the pimping condition. And now we could be able to calculate the Euler critical buckling load. And all the details you can find it from the lecture note 10. I have spent the long time, but it will be repeated in topic 11 and 12. It might be better for you to understand it. So that's for everything, and we will meet again by topic 11. Thank you very much. 감사합니다.